My name is Inder K. Rana. I am the instructor for Division 1 and 2 for the course MA 105 Mathematics 1. So let us come to the aims and objectives of this course. You must have already gone through something called calculus in your probably standard 10th onwards. It starts now. Yes? 10th, 11th, 12th, you go through what is called calculus and you have some understanding of what is calculus. So our main aim is to discuss logical developments of the basic concepts of calculus of one and several variables. Of course, you don't do several variables in your school education. In a rigorous fashion and discuss applications of these concepts. So this is the basic aim of the course. So more emphasis will be on conceptual understanding of concepts rather than just computation. Of course, applications form a part of any syllabus, so that will be there. So let me give you a brief history of calculus, a very short introduction. Normally, as we understand, calculus consists of two parts. One is differential calculus and other is integral calculus. Historically, normally when it is taught, we teach differential calculus first and then teach integral calculus. But historically, integral calculus developed first and then came differential calculus. So, the notion of areas, volumes of objects, how to compute the areas and volumes of various solids, attracted the attention of Greek mathematicians. So, real integration started in the Greek mathematics period, that was before Christ. Some of the mathematicians, or you can call them mathematicians or scientists or whatever you want to call them, are Antiphon, Euclid, and then of course Archimedes. So roughly, of course there are many others, but these are the main persons, main philosophers, scientists of that era who can be named as having contributed to calculation of areas and volumes. The real problems of calculus started in the 17th century. So you can see almost for 2000 years there was hardly any development as well as calculus was concerned. And the problem came because of various political and other considerations. The problems were in mechanics, describing the motion of a particle mathematically. How does one physical quantity, that is the motion of a particle, can be described mathematically? In optics, the need to analyze the passage of light through a lens, which gives rise to the problem of finding tangent and normal to surfaces and curves. You must have all done experiments in physics. A ray of light hits a lens, strikes the surface, right, with some angle. What is that angle? If two lines intersect, we know what is the notion of an angle. But a line intersecting a curve, which is not a straight line, what is the notion of angle? How to define it precisely? So those are the problems faced by the mathematicians in 17th century. Then the problem of in astronomy was a favorite subject for almost any physicist and mathematician, to know the positions of planets, the distance from the Earth, when it will be closest to the Earth, when they will be in a line, and so on. So all those calculations require mathematics, and that gave rise to the concepts in calculus. So these are some of the problems. Computing areas and volumes, I have already mentioned that. I think by now all of you know that calculus, the foundations was laid independently by two mathematicians. I shouldn't call them mathematicians. One is, of course, Sir Isaac Newton, and the other is Leibniz. Because I corrected myself saying that both are mathematicians, or both were mathematicians. Newton was trained to be a scientist by his education. He was trained to be a scientist, a physicist and a mathematician. But Leibniz was not trained to be a mathematician. He was what we normally call as IFS officer, Foreign Services officer. He was a French diplomat going in various countries, talking about politics and various other relations between France and other countries. He was a French. And the story goes that in one of these assignments in England, he met Huygens. Have you ever heard about Huygens in physics? Huygens principle of wave propagation. He met Huygens in some party, and he got so fascinated by mathematics he was talking about. He said, I want to learn mathematics. And he started learning mathematics. A diplomat. And gave the foundation of calculus, independent of Newton. And he published it first. And Newton did not publish his work. When Leibniz published his work, Newton realized that this I have already done it. Similar thing. So he said, it is my work. So, but people realize that both have done it independently. So the credit goes to both of them, Isaac Newton and Leibniz. So here is a picture of Newton, and here is a picture of Leibniz. Nowadays, these things, history and pictures, you can always go on the net and search and find very easily. So they are not a big deal now. But it's interesting because you have to sit down on the computer and do surfing about such things rather than playing a game or something else. So that requires effort. Anyway, why I mentioned Newton and Leibniz was they gave foundations to calculus, but their work lacked rigor. It was more heuristic, more intuitive. Foundation was not on solid grounds. The principles were not very clear. What are the assumptions they are making and what are the conclusions they are drawing? It was not very clear. In mathematics, in any science, we want to say if P then Q. Right? If you assume P, then Q happens. But there it was more slightly hazy. Assumptions were not very clear. So from that point onwards, mathematicians started wondering about what is the problem with the work of Newton and Leibniz, how it can be made more precise, what is required mathematically. And for about 300 years, maybe 200 plus years, it sort of people deliberated about it, thought about it, and came to the conclusion that if you want to give a rigorous foundation to calculus, then one has to understand the following concepts. Now look, what are the concepts one has to understand? The concept of a real number. If you want to understand calculus well, you have to understand what is the real number. If I ask you what is the real number, what you will say? Yes, what you will say, what is the real number? Any number which is rational or irrational is called a real number. Complex is called real number? No, I don't think so. Yes? Any number which can be represented on the number line. So the question comes, what is number line? You see now, you see the foundations, how the foundations come into picture. Yes? Anybody else like to say what? Please feel, when I ask questions, feel free to say something so that I know where you stand and how much I want to say. Yes? Yellow t-shirt. Yes? Say something about real number, what you have learned, what you have thought about real numbers. No? Anything? Same what he says. What he said. Tell me what he said.
Real number is a number which lies on the number, which can be plotted on the number line.
Plotted on the number line. So you are giving a geometric definition of real number, which before Christ, Euclid or Archimedes also gave notion of a number. Yes, somebody else would like to venture and say something? Yes?
That can be represented as a fraction.
A number which can be represented as a fraction. Yes? That is a part of real number, you will say, right? Something more is there. So you see, already we know, yes?
A decimal number which has a
Keep sitting and answer. Yes, decimal number?
fraction which has a terminating or non-terminating.
Good. So there is something more he is saying. Now the question comes, what is a decimal expression? Right? So you are defining a real number in terms of a quantity which has to be defined. What is a real number? What is terminating? What is non-terminating? Right? For example, 1 by 3 you would like to call as a real number. Right? Because it's a fraction. And what is the decimal expansion you would like to write? Point 3, and you either put a bar, that means you are covering your ignorance. You don't know what is happening after that. right? How many 3's you put, you still don't know what is after that. It's like putting under the carpet, okay? Dot, dot, dot. So you have to understand, what does that mean? There's a concept of infinity coming there now. Dot, 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 infinity. What is infinity? So it leads to many foundations, right? Foundational questions, fundamental questions. So they realize they have to understand what is a real number. That was the first problem. Then they have to understand what is a function. What is the concept of a function? What should be called as a function mathematically? They had to understand that. This was the second problem they realized one has to understand. And third is the concept of limit. So these are the three concepts to understand, give solid foundation if you want to study calculus properly. Okay? So we will go briefly about these things before we go on to calculus. What is a real number? Even what is the number 1? What is 1? Try to define what is 1. You start looking now, right? What is 1? You don't know the answer. It's difficult to answer what is the number 1. Right? So, and it's a part of real numbers as we understand, our understanding goes. Right? We deal with, I have got 1 shirt, I have got 2 pens, I have got 500 marks, my rank was 3rd in JE, and so on. We talk about numbers. What is that mathematically? We don't know. So defining what is a real number is a slightly complex process, which we'll not do in this class because that itself will take about 1/3 of the semester. We will assume that we already have got that set. Those of you who are interested in knowing this thing, there is a book in the library called From Numbers to Analysis. It's not, I'm saying that go and read that book, okay? If at any time you find this concept intriguing and you have time beyond your regular classes and you are motivated to know more about such things, you can read that book, From Numbers to Analysis, okay? So we'll say that real numbers are elements of a set which will denote it by this letter R, okay? It's not the usual R. To distinguish between the English letter R, we put these 2 bars to indicate it is a special set, right? Whenever we write this set means it is a set of real numbers. And what do we want to do with real numbers or with numbers? Obviously we want to add them, we want to multiply them, we want to compare numbers, and then we want to do something more. Let us see what are the things we want to do. So I am giving you what is called axiomatic definition of real numbers. Real numbers is a set R whose on that there are some algebraic properties. Algebraic properties are defined by 2 binary operations. All of you understand these terms called binary operation? There is a binary operation of addition defined on this set R, x comma y, the pair goes to x plus y, and similarly there is a multiplication which says x comma y goes to x into y. Okay? So these 2 operations are called addition and multiplication, and they have the usual properties that we are familiar with. Okay, so we list them as properties of these binary operations. So with the usual properties, I'll just quickly go through because most of you know it. So x plus y is y plus x, x into y is y, the commutative property. And then there is a associative law for multiplication and addition. There is a distributive law for how multiplication behaves with respect to addition. The distributive law is interaction between the 2 operations, addition and multiplication. How do they interact with each other? And then there is a special number called 0, denoted like this, and there is a special number, I will call it as 1, because we are going to call it as 0 and 1 eventually, with the properties that special number added to x, any number x gives you x, for all x belonging to R, and that number, other number multiplied by x gives you x for all x belonging to R. Right? These 2 special, they are special elements. So the element 0 is read as 0 and is called additive identity, and 1 is read as 1 which is called multiplicative identity. Then of course there are what we call additive inverse and multiplicative inverse with respect to those two operations. So there is an additive inverse for every real number, and for every non-zero real number there is a multiplicative inverse. So that gives you, if a number 1 is there, right, there already 3 is there, right? What is 3? Okay, I will come to that probably a bit short. Let me. Then there are order properties. We would like to compare numbers, right? Given two numbers, we like to say one is larger than the other. Human beings want to do that. I have more money than you, right? I am taller than you, and so on. So, requirements, physical requirements of the society had motivated human beings to define what is called order. So, this set of real numbers has a order defined on it. What does it mean? This is an order which is denoted by this symbol with the properties that given any two real numbers x and y, at least one and exactly one of the properties hold. Namely, you can compare any two real numbers. Either x is equal to y, or x is smaller than y, or x is bigger than y. One of the properties and only one of the properties will hold. This is called law of trichotomy. Right? Among these three, one and exactly one of the properties will hold. And of course, how does this order behave with respect to addition and multiplication? We have to say that. Because they all are going to live in the same house, real numbers. How does order behave with respect to addition? How does order behave with respect to multiplication? So, if you take two numbers, x and y, both are bigger than 0, then their product and sum is also bigger than 0. Right? 0 is that special number, remember. So, if you compare x and y with 0, if both are bigger than 0, right, then the product also is bigger than 0 and sum is bigger than 0. And of course, there is a third property that if x is bigger than y and y is bigger than z, then x is bigger than z. Right? If you can compare 2 and then it's bigger, so this x must be bigger than z. So, these are the properties of the order on real numbers. So, one was algebraic properties, other was order properties. There are two more properties. See, till now whatever we have done, that is valid for rational numbers also. Right? You can add rational numbers, you can subtract rational numbers, you can compare rational numbers. All those properties are true. So, in what way this differs from rational numbers? That we have not yet described. So, those properties are going to be described a bit later. We have to develop some more machinery for that. One is called Archimedean property, which does not actually require that property is true for rational numbers also. Probably we'll come to it later. And the fourth is called completeness property. So, these two properties, one is called the Archimedean property and the other is called completeness property. These two properties will describe in a short while in coming 1 or 2 lectures, because we have to develop some more machinery for describing these properties. Right? Okay. So, we will describe that. So, now let us see. I said axiomatically we have given you a set. Where are our natural numbers in that set? One can ask the question. Where are our natural numbers? Right? But you recall, already we have got a number 1, the multiplicative unit. Now, you can add multiplicative unit to itself. Addition is allowed. So, you will get something new, that is called 2. You add once again that multiplicative unit to 2, you get a new number, call it as 3, and so on. You get all natural numbers from the number unique element 1 using the property of addition, right? And you get a set. Okay? And one can say the set of natural numbers is the smallest subset of real numbers which have the property that if a number belongs to it, if a number 1 belongs to it, and any n given n plus 1 also belongs to it, it must be the whole of the set. That is what is called principle of mathematical induction. So, that gives a definition of natural numbers, a property of real numbers in axiomatic setting. Okay? So, let us just natural numbers 1, 2, 3 and so on. So, they are 1 plus 1, 2, 2 plus 1, 3 and so on. Once you have natural numbers, you can construct integers by using additive inverse and 0. All natural numbers have got additive inverses along with 0, that gives you integers. Once you have integers, you can construct fractions by using multiplicative inverses, right? Every non-zero number has a multiplicative inverse, so you can multiply them. So your numbers of the form n into m inverse, where m is a non-negative, non-zero number. We can make it actually non-negative n any integer. So that sign you can always shift it to the numerator, right? Denominator you can always assume to be a positive integer. So rational numbers, these are called the rational numbers. What is not rational is irrational. Still I am not defining what is irrational. You see the fallacy. Because we have assumed already there is a big box of real numbers and part of it is rational, whatever is left is irrational. But let me give you a slight feeling for it. So as somebody said, we can represent numbers on the line, right? Every number on the line is a real number. So this is how numbers are represented on the line. You have all done it. So draw a horizontal line. That is how Greek mathematicians understood numbers. So start with a horizontal line, make equal marks, call them as 1, 2 and so on. They are called natural numbers. So natural numbers are represented as points on the horizontal line, and then you go on the other side and mark 0, minus 1, 2 and so on. So all integers are plotted on the line, horizontal line. From that you can plot now fractions, p by q, right? The pth part, so you want to plot what is p by q. So what you will do, look at the integral part of the number, say 21 by 7, what is that equal to? 3. Let us say 3 plus half, 3 and a half, 7 by 2, that fraction. How do you represent it? Go 3 units and then go half of the next unit, right? So all fractions can be plotted on the line. Now this is the stage where mathematicians started wondering. So what we are doing, we are taking the set of all rational numbers which we understand and throwing them on the line. They go and sit on the line somewhere, right? So the question is, does it fill whole line or not? You understand the question? Intuitively, I have taken the rational numbers and thrown them on the line. They go and sit on the line. Does that fill every point on the line or not? That is the question. No. So let us try to show by an example that why it does not happen. Okay? So this is a very well-known example. So what you do, this is a number line. This is the point 1. So draw a square on the number 1. Geometric construction only. Make a square with side as 1, 0, 1. Look at the hypotenuse and whatever is the length of OA, mark the point Q on the line. So OA is equal to OQ. Okay? Now what is that point Q? Question is there a rational number which is sitting at the point Q or not? Right? If every point on the line represents a rational number, then what is the rational number that the point Q represents? Mathematically, what is the length OA? How many magnitude? What is the magnitude of OA? I don't know what is root 2. But I know OA square by Pythagoras theorem is equal to 2. The square of the length of OA is equal to 2. That much I know Pythagoras theorem. So this point Q represents a number whose square is equal to 2. If at all it represents a number. And all of you know there is no number, no fraction whose square is equal to 2. Yes? The equation x square equal to 2 cannot be solved for x to be a rational. Right? Everybody knows the proof of that? Try to construct a proof yourself. It is very easy. Try to construct a proof that there is no rational number without going and looking into a book now. Okay? It requires only factorization of numbers, prime factorization. Every number can be written as a product of primes, right? Use that to show that there is no number, no rational number which represents the point Q. That means there is no rational number whose square is equal to 2. So this point must be, if you want to say that every point on the line, right, is a number, then what kind of numbers it represents? Those are precisely the points which are going to represent irrational numbers, right? Still irrational is not defined, okay? because definition requires more work. So they are called irrational. But it's quite clear that geometric notion of putting all numbers, rationals on the line leaves gaps, and filling those gaps mathematically is the construction of real numbers. That process, how to transform that geometric idea that every point on the line is represented by a number. See, geometry being made mathematics. Geometry is construction only. But saying there is no number x square, p by q, whose square is equal to 2 is mathematics. Right? That is arithmetic. So how to get arithmetic out of geometry? So how to say that you take any point on the line that will represent a number. What is that number? How to construct that from rational numbers? Okay. So that is a property which took mathematicians about 300 years to resolve. So geometrically, we'll say that I hope there is something works. I can show you if it works. It is just to make the class a bit lively, that's all. Nothing very great, it's just a small animation saying what is a number line. The number line is make plot numbers 0, 1, 2 on the side, integers, rationals 1 by 2, and then everything is the real numbers. Okay. So it's a small movie for a break. Okay, in the usual class. Okay. So in the number line, what very important property vis-a-vis rationals and irrationals for the numbers, which is very important and which is used very often, namely what is called the denseness of rationals and irrational numbers on the number line. So when you are throwing the numbers on the line, they go and sit on the number line, right? But how much position they are occupying, how much space they are occupying on the line, you can ask that question. And it says that they sit densely. That dense means what? Given any two real numbers, any 2 points on the line, there will be a rational number in between them. Given any two real numbers x and y, if x is not equal to y, if there is some distance between them, there will positively be a rational number. That means rational numbers are everywhere. Yes? Intuitively it says rational numbers are everywhere on the line. Okay? And same way, irrational numbers are also everywhere on the line. That given any two real numbers, there is a irrational number sitting between them always. I don't know how many of you have come across this fact or not. Rational numbers dense is normally stated in the books. But irrational numbers are also dense. That not many books state that. So try to construct a simple exercise. Given any two real numbers, how to find a rational number in between them. Take two real numbers x and y, x less than y, then there is an irrational number in between them. Right? Find that irrational somehow. Demonstrate. That is what is mathematics. You don't know what is x, you don't know what is y, but still I can demonstrate that there is an irrational number between x and y. For example, if x is rational, y is rational, what is the number in between them which is irrational? X plus y by 2. Simple. I have proved it. Because if x is rational, y is rational, x plus y is rational. So x plus y by 2 also is a rational number, and that lies between x and y. So proof. Without knowing what is x, without knowing y. That is what is the beauty of mathematics. Without knowing actually what are the things, you can prove things about them. Similarly, try to prove if x and y are two real numbers, x less than y, then there is an irrational number in between them. Okay? Try to prove it. So that is the property of denseness of irrational numbers. Then there are some important subsets of real numbers which we will be using in our course. They are called intervals. A part of the line. Geometrically they are part of the line. Segment. Right? Part of the number line. The segment of the number line. So one is open interval. So it is all numbers x say that they lie between a and b. Given two numbers a and b, look at all the numbers x say that a is strictly less than x, strictly less than b. So all these points, they form a set, and that set is denoted by open bracket a comma b, and that is called an open interval because the end points are not part of the set. Similarly, you will have what is called a closed set. So A less than or equal to X less than or equal to B. That is called a closed interval. Both the endpoints are included. So in the picture, this will be the open interval, right? All points in between, and excluding A, excluding B, and this is the closed interval including. So this is the square bracket indicates that we are including that point. Of course, you can construct other kind of intervals. You can include one endpoint and not the other. So all possible variations, I will just list them, right? This is something important, I think I should say. Look at all numbers, given a number A, look at all real numbers X such that X is bigger than A, strictly bigger than A. This is a subset of real numbers. That subset is denoted by A comma plus infinity. So geometrically what you are doing is A is given to you, you are going on the right side of A, all the points which are on the right side of A, but A not included because we are saying A open, right? But don't make the mistake of saying that infinity is a number. That plus infinity is a number. It is just, we are using it as a notation to indicate that we are looking at this set. It is just a notation, convenient symbol for writing it. It is not a number, it is not a real number. Okay? Similarly, you can have it on the left side. You can include the point A and so on. So let me just go over all these things. Out of this, something very important and useful for us. Given a point A, look at all the open interval with left end point A minus delta, the right end point as A plus delta. That means at the point A, you are going on the left side by a distance delta. From the point A, you are going on the right side by a distance delta, and you are not including the endpoints. That is called a delta neighborhood of the point A. Right? In some sense, we are describing all the points, right, in a neighborhood of, in the locality of A, with delta locality you can call it. Right? That is a way to understand these things. That's why the word neighborhood comes. So this is numbers. Till now we have described only the numbers. Now let us come to what are called functions. Okay? You will be surprised, till 1700 and I think 30 or so, mathematicians did not know what is a function. They thought function is something whose picture can be drawn. And what is a picture? You take some x-axis, take some y-axis, and start at one end and draw something, right? That is a function. So function is an object whose picture can be drawn in a sense, right? So people had heated discussions whether while drawing a graph you can lift your pen and start somewhere else or not. Whether you can do that or not. People said you can't do that, then it's not a function. Or you are going, you suddenly put a peak somewhere, right? A corner kind of in the graph, and then go and say that is also not allowed. So these are the kind of conceptions people had or mathematicians had till 17th century. It was much later by the mathematician you might have already heard named Cauchy. Have you heard about the name Cauchy? A mathematician, again a French mathematician, who defined what is called a function. And he said it has nothing to do with the graph of the picture of the thing. It is a formula. Function should be a formula. Anyway, so we'll go over that. But now it's very easy. If you ask somebody what is a function, he'll say it is a correspondence. Yes? Dot, dot, dot. Fill in the blanks. Is a correspondence from a set A to a set B. For every element of A, it assigns a unique element of B. And that correspondence is called function. In less than a minute, you have defined what is a function. But understanding of this concept took more than 200 years. That this is what is a function. Okay? So we'll take that definition because otherwise I'll go too much into foundations of mathematics. So we'll treat function as a assignment or a correspondence from a set A to a set B. So this is a set A, this is a set B. And what does it do? It takes a point X and throws it on some point in b, which we call as f of x. So this f of x is called the image of x. Okay, so x belonging to a goes to f of x belonging to b. So if f of a is equal to b, then you call b as the image of a, or a as the pre-image of b. So all of you know this, what is called the domain of the function, what is called the codomain. Yes, everybody knows all such things. They're all done in school now. But I'm just revising so that our knowledge and our notations are complete for the remaining part of our course. So range of the function, so that is the set f of a, say all the images of a in the domain. And then what is called the graph. Graph is not a picture. Graph is a set. Graph is a set. It is not a picture. We represent everything as a picture because human beings understand pictures well. Right? If you say my friend looks like he is 6 feet tall and about 50 kg and fair complexion and this, something comes to the mind of the person who is listening to you. But if you show him the picture, I now know this person very well. Right? So that is the difference between a function, a formula, and a picture. So graph is a set actually, but we can represent it as a picture. So how would you represent it as a picture? We draw two lines, domain as horizontal line, range as the vertical line, and then plot. Then plot the points a comma f of a. That is a subset of the cross product of two sets, a cross b. Right? A is a set, b is a set. You can find a cross product of sets, which is again a set. Okay? So graph is a subset of the cross product. So in mathematics, everything is a set. Even numbers are sets. Okay? That is what everything is set theory in mathematics. From set theory, everything comes out. That is what is called foundations of mathematics. So graph is a set, is a subset of a cross b. So you can visualize this, as I said, by drawing one vertical, horizontal line, and so on. Then there is something called 1-1 map. Right? If different points go to different images, that is called 1-1. And something called onto. Every point in the codomain has a pre-image. Some point goes to that point. Range is whole of codomain. That is called onto function. And 1-1 and onto both, that is called a bijective function. Okay. Now let us define what is called a composite function, which is also useful in mathematics. F is a function which sends elements of a to elements of b, and g is something which sends element of c to elements of d, but with the property that f sends elements of a to a set part of b, but that is a part of c, that is inside c. Then g can operate that point and throw it else. Right? So that is what this is a. F takes the point x and puts it into a point f of x, which is a part of c. So b is part of c, and then g will take this point and take it to a point in there. So that is what. So you can go directly from a to the set d via these two paths. Right? So x goes to f of x goes to g of f of x. There is a wrongly drawn picture here. So from here to here, and that point g takes there to there. So that is called the composite function. Okay. Now all this was done to bring to a very important function for us, that is called the absolute value function on the real numbers. So absolute value function, it is a function defined on set of all real numbers. So domain is set of all real numbers, and the codomain is the set of all. What are these numbers? Positive, non-negative? Non-negative numbers. 0 is included. They are all non-negative numbers. So how is it defined? Intuitively, the idea of distance, the geometric idea of distance. X is a point on the line. You want to say its distance from the point 0, the special point 0. There is some distance. So that distance, physically a distance is always a non-negative quantity. Right? So it has to be non-negative. Whether it is on this side or that side doesn't matter. Distance is always same. Right? So we define what is called the absolute value. Geometrically it is the distance from the point 0. It is a number x itself if x is non-negative. And if it's negative, because the distance has to be right, non-negative, so minus of x, because x is less than 0. So minus x will be bigger than 0. Clear to everybody? So geometrically it is the distance of the point from the special point 0. And mathematically it is defined as mod x, or absolute value function. Absolute value of x is x if x is bigger than or equal to 0, minus x if x is less than 0. So this is the picture. So this is the point 0, this is the point x, this is the point minus x. So whether here or here, it doesn't matter, right? That is absolute value. So what will be the distance between 2 points x and y? You look at the point x minus y. You don't know whether x is bigger than y or y is bigger than x. Does not matter. Then we had order, and the order has given rise to the notion of distance. How is this order coming? How is this absolute value coming? It is coming from order. If you can compare x bigger than 0 or x less than 0. Clear? So it is a consequence of, because there is an order defined on real numbers, you get the notion of distance. So there is an important property of this function, absolute value function. Absolute value of x is bigger than or equal to 0, and it is 0 if and only if x is equal to 0. Does everybody understand this statement, if and only if? Yes? So it's a two-way implication. You say if P then Q, if, right, P implies Q, and if you want to say also Q implies P, then you say P if and only if Q, both ways implication. So it says that absolute value of x is bigger than or equal to 0, by, it's clear by definition, and it is equal to 0. When is it equal to 0? Obviously if and only if x is equal to 0, because if x is bigger than 0, then it is equal to x which is not equal to 0, and it is minus x which is not equal to 0. Again its value is x minus x which is bigger than 0. So if and only if. The second property, of course, absolute value of x is same as absolute value of minus x, that we have seen by definition. Then how does this function behave with respect to product? See, whenever you have a family, right, the real numbers, on which already addition, multiplication, order, whenever you define something new on that, whenever a new person comes in that family, you have to tell how is that person going to behave with respect to other members in the family. So same real numbers, we have got addition, addition, multiplication and order. So we have to tell how this, now we defined absolute value function, how does it behave with respect to addition and multiplication of numbers. It says if you take two numbers x and y and take their product, then the absolute value is same as product of the absolute values. Okay, doesn't matter whether you take product first and then take the absolute value, or take the absolute values and then take the product. All these properties are, you must have already proved these things in your earlier education. If not, take them as a small exercises and try to prove them, because that's how you will learn how abstract things are proved. For example, if you want to prove product of xy is equal to product x, product y, how will you start a proof? How will you try proving it? If I give you an exercise, proof product of xy is equal to absolute value is equal to absolute value of x into absolute value of y, how will you prove it? How will you start thinking? Yes? What will be your first step? Let me give you a similarity. You are staying in some hostel, say hostel number 2, and you want to go to Market Gate. Right? The problem is to go to Market Gate. What you will do? What you will start thinking? First of all, do I know the directions to go to that place or not? Now to go there, do I have a bike, cycle, or do I have to walk, or can I take a auto rickshaw from outside the hostel? Right? What are the possible ways I can reach that place? Because there is some distance, I have to travel that distance. What are the modes of traveling that distance? You will start thinking that way. So same way now if I want to prove this, I want to prove some property about absolute value function. Yes?
Let's take all the cases.
Good, very good. So why you should take the cases? That is the question.
Because it may be anything positive or negative.
Precisely, because absolute value function, you have to calculate what is mod xy, right? And that depends upon the sign of the product. So you are forced to divide your proof or your argument into cases. Cases where x is positive, y is positive, then x, y will be positive, you prove it, right? Case 2, x is positive, y is negative, and so on. So your proof will be, you will be forced to divide your argument into sub-cases. That's how you will start thinking about it, right? As I said, if you want to travel from your hostel to Y point, you will start thinking of mode of travel because you want to travel. So you want to prove something about absolute value, and you see how absolute value function is defined. How you can compute left hand side, how you can compute right hand side, and show both are equal, right? So try to write down the cases if you have not done it earlier. Now, for example, this is again the same property written in a different way, that for any number x, minus mod x is always less than or equal to x less than or equal to mod x, right? Because it's a distance, okay? And now this gives you a very simple consequence, that mod of x is less than y. Mod of x is less than y, that automatically makes y to be a non-negative number because x could be 0, okay? So if and only if minus y is less than or equal to x is less than or equal to y. So how simple things are proved by using simple definition only. This is what is mathematics about. You have some definition, some simple concept, using that alone you have to prove now something, okay? And once you have this, you have a very nice property with respect to addition. And that says, if you take sum of two real numbers and take their absolute value, that is not always equal to absolute value of x plus absolute value of y, but it is less than or equal to absolute value of x plus absolute value of y. This is what is called triangle inequality, because it has more meaningful geometric representation in the plane. The distance with, like in a triangle, the sum of two sides is always bigger than or equal to the third side. So that essentially, it comes from there, the word triangle. But this is, 6 is a consequence of 4, immediate consequence of 4. Because what you want to do? You want to show that mod of the number x plus y, you can call it some number, is less than some other number. Mod of some number is less than. You can see now. See, now you can see that 5 can be used in proving 6. This number you can call it as b. X plus y you can call it as a. So you want to prove mod of a is less than or equal to b. When does that happen? 5 says it will happen if and only if minus b. So minus of this absolute value sum is less than or equal to absolute value of x plus y, and that is obvious. So that is how you prove triangle inequality. So I have written down the proofs, but I have already discussed with you. So those proofs, so let me just go over them. So that proves so that is what I said. See, this is, so minus mod x is less than x less than mod x, right? Minus mod y less than, add these two, what do you get? That is why I said it is consequence of the previous one. If you add, you get minus mod x plus mod y is less than x plus y is less than mod x plus mod y. That says minus b is less than or equal to a is less than or equal to b for a non-negative number b. That means mod of the middle one is less than or equal to b. That is triangle inequality. So that's how simple, without going to cases, you can prove it as a consequence of this. That's how we do it in mathematics. You don't prove everything again and again. You have already proved something, you use that thing to build your next step. Right? Triangle inequality can be proved directly also by dividing again into cases. Right? X plus y bigger than 0, x plus y less than 0, then sub cases of that, x is bigger than y, y is bigger, all sub cases you can do it. But this is a neat way of doing that. So that is called the absolute value function. So let me just recall what we have done today. What we have done is, we defined axiomatically what are called real numbers. Right? We defined what is the notion of functions, and then the notion of absolute value function and its properties. Okay? So with that we come to end of today's lecture.